Right, okay. Hello, everyone. I'm Matteo. I am a postdoc at Chalmers University. So I'm enjoying this workshop very much. I'm learning new interesting things. And so my talk, the first part of my talk is going to be about, let's say, slightly different topics to probably the main focus, but I will try to motivate at the beginning that there is going to be a connection in the second part. So I hope that everybody can take some insights from the work we've been doing in the past 1.5/2 years. So this is works done in collaboration with some people at Chalmers. So Juliette and Christian are postdocs in the group of Professor Janine Schwesterser. And also Jakob Eriksson, a former master student, and Ludovico Tessere, who is a PhD student in the group. So the focus of my talk is going to be about electronic transport in quantum conductors. So these are, so you can imagine that you have a mesoscopic conductor and you have some electrons, for example, in your conduction band, and these electrons are kind of free to move around, and they will be connected at some point to some reservoirs where you define, as in the first Bibex slide, where you can define a temperature or a chemical potential. And these electrons will carry, of course, charge currents. And that's the usual quantity that people look at to characterize the transport properties of mesoscopic devices. But I will also focus on heat and energy transport. So first of all, why care about heat transport in these systems? So when you have a quantum conductor, you have situations where basically the system is so small that the scale of thermalization is larger than the system size, and so you cannot define in internal local temperature and internal temperature. You just have the two reservoirs, and that's it. And so this opens up opportunities to try to explore properties of quantum systems, to use them, for example, as nanothermal machines, thermoelectric effects, and so on. And so what I put on the right of the slide was a realization of an engine made with suspended, with a quantum dot, basically, which is realized here with a suspended carbon nanotube. And so this, of course, is interesting for exploring quantum thermodynamics in this kind of systems. And also, the main focus on this talk is going to be non-equilibrium fluctuations. And in equilibrium, we all know that the fluctuation-dissipation theorem says that the noise is proportional to the conductance, and this is a nice connection, but it also means that measuring fluctuations doesn't tell much more than just doing, for example, conductance measurements. Whereas when you go out of equilibrium, the noise has all sorts of richer features. So I put here 3 examples. So you can use the noise to characterize nanoscale devices. For example, this review here discusses all sorts of properties, and in particular, how you can use noise measurements to make thermometers, for example, so to probe the temperature of your electronic sample inside a cryostat. On the more exotic side, in the 90s, shot noise measurements have been used to detect quasiparticle charges in systems where the excitation are fractional excitation. So that would be the quantum Hall effect. And this was done by noise measurements as well. And more recently, in the context of, let's say, thermal transport, there are proposals saying that noise can also be used to probe local temperature gradients. So the whole idea, let's say the origin of the works I'm going to talk about are represented in this slide. So this is a work that Janine did in collaboration with Rob Whitney, who was also mentioned before in this workshop, and Rafa Sanchez in Madrid. where they had this idea of proposing a system that exploits non-equilibrium states as a resource. So what this slide represents is two terminal systems. So 1 and 2 would be two macroscopic fermionic reservoirs. And then there is a non-equilibrium part of it, which is schematically represented here with a non-equilibrium distribution. So the distributions of the two terminals 1 and 2 are Fermi-Dirac distribution, and this is just something else. And the point was, can we exploit this non-equilibrium distribution to make some useful tasks? So for example, to do cooling between terminal 1 and 2, or to operate the system as an engine. And the point is that, yes, you can, and also you can achieve that while on average you have no transfer of current between the non-equilibrium resource and the system. So I will come back to this in the second part of my talk. And so these results have been published in this PRL in 2019. And so our idea was, what about the fluctuations? Because this is, of course, an average effect. So in average, you have no current exchange, but what is the role of fluctuations? So with this in mind, we took a long detour and we consider much simpler systems. So you start from a situation with just two terminals, and the properties of your conductors are encoded in a transmission function that simply tells what is the probability that you can be transferred from one side to the other of the system if your electronic incoming states have energy E. And so we started to try and characterize how non-equilibrium fluctuations behave in this system under the condition that we have a zero average current, because we had in mind to characterize the properties of that system where you, on average, you don't inject any particle or energy current. And so this is going to be the first part. And yeah, so this also further motivation. So this zero current condition seems a bit artificial, but apart from this system that we had in mind, also when you characterize, for example, thermoelectric properties in a thermoelectric conductor, when you, for example, apply temperature gradient, you also develop a voltage bias that counterbalance the current. So you will, at the thermal voltage, you end up in a situation where you have zero net current. And also, even this is an equilibrium property, at equilibrium, you have the fluctuation-dissipation theorem, as I mentioned, and there have been recent works trying to generalize fluctuation-dissipation theorems to out of equilibrium situation, and this has been shown in some cases to be feasible precisely when you have a zero current condition in a part of the system. Yeah, so this is the outline for the talk. So in the first part, I will talk about how we can characterize the shot noise in the absence of current and how this obeys general bounds for charge and spin transport, and instead no such bounds are found for heat or energy transport. And in the second part, I will come back to the system I was showing before with this non-equilibrium system working as a kind of daemon, and try to also study the role of fluctuations there. So the second part is still work in progress. We have first block of results, which I'm going to show, and we are still in the process of figuring out further things. Okay, good. So let's start. This is just to set the stage. The system we have in mind, as I said, two reservoirs described by Fermi functions, and in the middle you have a transmission function. And we are considering non-interacting electronic transport, which means that we can use the framework of scattering theory, which is known to also be thermodynamically consistent and respect the second law and all sorts of nice properties. So in this kind of situation, the currents in the system are given by these simple formulas, where you have the difference of the Fermi functions determined in the transport window, and the transmission probability, which is a number between 0 and 1. And this little x here is just a shorthand notation to describe simultaneously three different transport properties, so the charge, the heat current, and also the spin current, where you basically count the number of particles going in from left to right with a different sign depending on their spin polarization. And when it comes to fluctuations, we can, broadly speaking, distinguish two kind of contributions. First is thermal noise, which is due to a finite temperature in one or two, one of both of the reservoirs. And this effect also persists in equilibrium. So you have this characteristic factor here, which can be readily interpreted as the probability that an electronic state is occupied and also that you have a hole. And so this is, you know, an effect coming from the randomness in thermal excitations. And yeah, and so this thing here survives even when the system is completely in equilibrium. On the other hand, you have shot noise, which is usually interpreted as caused to the randomness in a current partitioning. So now here you apply non-equilibrium, you have a stream of particles incoming to your barrier in between, and at the barrier, particles can be randomly transmitted or reflected, and this generates noise. And so here you see, instead of this factor here, you have this characteristic factor there, which is also interpreted as this partitioning factor. So it's probability of being, for example, transmitted times the probability of being reflected. The point is that even if the shot noise is usually interpreted as usually associated with a current, from the expression, you see that what's really needed is just the difference between Fermi functions. So you can achieve this even when the system doesn't support a steady state of current. And so this is what we wanted to understand a bit better. And an example, there have been a couple of recent papers, so these two, 2018 and 2020, where in tunnel junctions, they have measured an additional effect in noise signal due to temperature gradients, and this also happens without the current flow. So this is what we want to understand a little bit better. So the first thing is that we want to, yeah, as I said, generalize to different bias combination on equilibrium configuration and different current, rather than what was provided in this paper, which was about charge transport under a pure temperature gradient. So the first thing we did is we consider the simplest case, constant transmission. So you have a uniform probability to be transmitted, and we ask what are the simplest possible bias combinations that fulfill the zero current condition. So here for charge transport in the top row, spin transport in the middle, and heat or energy transport in the bottom row. And so for spin and charge and spin, you can achieve a zero current condition with just applying temperature bias or a spin imbalance. And for the spin, instead, you need either voltage bias or a temperature bias. And for heat, you just need a combination of the two. And in this very simple situation, so we can derive simple, very simple expressions for the total noise, which look like this. These are not particularly informative, but we can see that all of these formulas can be rephrased into this form, where J is nothing but the particle influx that's coming from the hot to the cold reservoir. So this was kind of already known. So, but I would say we recovered this result, and we were particularly interested in characterizing the noise in this situation, because in one of the previous paper, this one here, they had noticed that when you do noise measurements in this regime here, you find a factor log 2, which they were trying to interpret as some kind of erasure principle, because they say you have like an excitation which comes from the hot reservoir, and then when it transferred, it's kind of erased in the arriving reservoir. we didn't particularly understand this interpretation so well, and what we actually think is that it's nothing but if you write down the particle influxes coming from the hot to the cold, then and you calculate this particular quantity for a constant transmission, and just with the temperature bias, you get this factor log 2. It's just an integral of the Fermi function. So there might be some kind of relations with the erasure principle, but this is what we found here. And now coming back to the comparison between shot and thermal, in this situation, when you just have a thermal gradient, the system is electron-hole symmetric, so there is no charge current. And you calculate the noise, and you can split it into these two contributions. So the part which is linear in the transmission is the thermal contribution I was mentioning before, and the part with this characteristic D1 minus D factor is the shot contribution. And so the relative magnitude is such that the thermal noise is larger than the shot noise. And this is for a very particular case with a constant transmission. And we wanted to understand whether under the zero current condition, this relation is always verified, whether this is a general property. It turns out to be the case. So what we did was now consider a system where the transmission is arbitrary, and also the possible bias combination is arbitrary. And just by clever inequality, exploiting some inequalities, this was mainly done by Ludovico, we could prove a bound. So for any transmission function, temperature biases, and at zero current in a spin symmetric system, you find that the shot noise is always bounded by the thermal-like component of the noise. And actually, there is also a tighter bound where here this theta, H, and C are the thermal component of the hot and the cold reservoir separately. So this only relies on the properties of Fermi functions, and the transmission function is between 0 and 1, and can also be extended to the case when you have many conducting channels in your system. Then we moved on and we added spin in the game. So here the conditions are slightly different. So what you do is you replace here this spin symmetry with this particle hole symmetry, and then you find basically the same result. So in this part here, you have a combination between, let's say, temperature and voltage biases, and here you have a combination of temperature and spin imbalances, but still the same inequality holds there. So when these inequalities are broken, this indicates that these symmetries that we need for the proof are broken. And this also means that the results do not extend to multi-terminal systems, because with a simple case of spin preserving scattering, you can argue that a system which is not spin degenerate can be effectively seen as a multi-terminal system.
Maybe I can ask a question.
Sure.
About this. Can I understand this result in the sense that if you apply thermal bias, then the current must be proportional to that temperature difference, and the shot noise is proportional to the current. So that's why it's like the hot temperature minus the cold temperature. Is that?
Sorry, say it again.
So if I apply a thermal bias across my contact,
Yeah.
I know that the current is proportional to that thermal bias times the thermal conductance.
Yeah. Yeah.
Right? And so we're looking at heat current here, or is this just
Here is the charge current and spin currents here. So no heat now.
It's like my Seebeck coefficient. Right? So the charge current is like the Seebeck coefficient times the thermal bias.
Yeah.
And then the shot, usually in these mesoscopic samples, the noise power is your frequency is proportional to the charge current, right? Times the Fano factor. And so this is why I think we understand that why it's the difference of the two temperatures.
I guess you could see it like this.
Yeah.
I would also like to stress that this also extends to like nonlinear regime.
Yeah, but
So
I think even if you extend to nonlinear regime, how does the power of delta T? the heat current, you can write it in terms of delta T squared.
Yeah. Yeah, you could do it like this.
Yeah, and then the thermal current is just obviously this must be the sum of the two temperatures, right? You have independent fluctuations in both.
Yeah.
Okay.
Right. So this was about spin and charge and then spin currents and their fluctuations. And here I'm showing just an example where this bound can be kind of saturated. So here is an example which shows resonant transmission. So here just a tiny little peak at some point in energy at position epsilon. And what I'm showing here is the ratio between the shot and thermal components of the charge noise. And whenever you see yellow, the ratio approaches 1. And so this happens where the resonance is very narrow. And whenever you see green instead, so this area here, you go back to the result I was showing before for constant transmission. That's just because the resonance is so broad that effectively this transmission looks like a constant compared to the other energy scales in the problem. And in the right plot, instead, I'm showing you the bound with the difference of thermal noises rather than just the full thermal noise. So the bound with the full thermal noise would be just this constant line, and the dotted line is the improved one. And so this was just to show that whenever one of the two temperature is not extremely small compared to the other, this improved bound actually captures much better the behavior of this noise. And the other bound would just be, I mean, it's still verified, but it's not very tight. Yeah, okay. So this was more, I will probably skip this and just briefly mention that we also extended this result for charge transport when we consider finite frequency noise. It was more like a further analysis and yeah, I would say, yeah, in the interest of time, I think I will move on. And so now coming to the heat, we repeated the same analysis, and for constant transmission, you can again find a similar expression when you separate into thermal and shot components. And you find again that this coefficient here is just a given function of this this bias here that is needed to compensate for the heat current that would flow in the system. So that would be the thermal voltage. And in this case, again, we see that the thermal noise is larger than the shot component. However, this result does not extend to an arbitrary conductor. And here, basically, the crucial difference is that when you're talking about energy transport, of course, the transported quantity depends on energy. It's kind of obvious, but this thing is just enough that in the noise, you find this extra energy squared factor. And with this, you can engineer a transmission which will enhance the shot component and kind of suppress the thermal one, or at least keep it constant. So let me explain this to you briefly. So here I am just considering a particular example of a transmission, which is non-zero here in this region and here is 1. Here it's whatever value between, let's say 1/2, and then 0 again. So in this high energy region, the difference between the two Fermi functions is quite large. So this part here is kind of enhanced. And you have exponentially small thermal noise because this function drops very quickly. And here it's close to 0 and the other as well. In the low energy region, instead, there's where the main contribution to the thermal noise comes from. And these two separate regions are also those which allow to compensate the heat, where the two flows of heat compensate so that you have 0 current. And so basically, so the point is that now if I increase this gap here, just by exploiting this E² factor, I will increase the contribution of the thermal noise because I'm moving towards higher and higher energy. And this part here will instead remain kind of constant. And so that's why the thermal noise will be independent of this gap, whereas the shot noise will increase. And this is indeed what we observe with a gapped transmission function that looks like this, or this is another example. And so you see that by increasing this gap, the ratio between the shot and the thermal noise just increases with energy. So just this simple consideration that you have transported quantity which depends on energy makes it so that there is no bound for heat transport. So this was about the first part, and now coming to the second part. Yeah, so here I want to focus and to go again to the system I was mentioning at the beginning. And so let me repeat what the idea was. Here we want to use a non-equilibrium states as a resource, and the mechanism of how the system works would be that the resource provides a non-equilibrium input, which is exploited into the working substance to perform useful operation. For example, make a refrigerator or run an engine. And we also impose that there are no net currents. Why so? Well, because then if there are no particle or energy currents between the end part and the working substance, then it's kind of reminds in a sense of a daemon, because you have no input, no work done on the system, and still you can produce something useful. And of course, the paradox is resolved quite quickly, because the point is that this end part is a non-equilibrium system, and there you can have the entropy production, which will compensate for the entropy reduction that you get into the working substance when you, for example, run it as a refrigerator. Okay. So the motivation to do that is because in quantum systems, we would like to understand how to exploit non-thermal states, and then eventually also quantum resources to see if there is any advantage in using this over conventional thermal states. And also because you can imagine that in small scale systems, you have also access to non-thermal states quite easily. And so in principle, if one understands how to exploit them, one can kind of recover some waste energy, which can be very non-thermal. And for a fundamental point of view, I also want to stress that I said this reminds of a Maxwell daemon, but the crucial point here is that in my whole description, there are no interactions whatsoever, which means that feedback cannot be the mechanism that explains how the system works. So here it's a purely non-interactive system, so no feedback can be present. Okay, so then a possible implement. This is just an example. Okay, so we wanted to we have to start from somewhere, and so this is a simple way where you can by hand implement a non-equilibrium distribution, and this is very simple. So I'm just introducing now two additional reservoirs. These 3 and 4 are thermal, and I'm going to mix them by here, let's say a scattering region, and here in this particular case, just an energy dependent transmission, such that here I have a finite probability of being reflected like this, and also a probability of being transmitted from 4 to here. So what arrives at this point is like a mixture of 2 thermal distributions, which by itself is non-thermal, because you cannot define a common temperature. Yeah, so this was just an implementation that Rob, Janine, and Rafa have proposed, and this is based on an electronic system. There is also another one that they propose based on some optical device. Okay, and also the important thing here, this interface transmission determines how coupled or decoupled the daemon and the system are. And you can imagine that if they are totally decoupled, then there can be no fanning effect. Okay, very good. So the average current description is the following. So you can simply write down an expression, simple expression for the current flowing into the system. And here this T beta alpha is the transmission probability from going to terminal beta to terminal alpha, okay? And as long as you stick to average currents, you can map this system with 4 terminals or even more to this effective description when you just have a working substance with 2 terminals and an effective distribution. And in this case here, as I was mentioning before, you can basically see that this input non-equilibrium distribution is just a mixture of 3 and 4, weighted by this transmission probability, which depends on energy. Okay, and then this is an example when the system is operated like an engine. Here, the transmission is chosen to be a step function, which you can do with a quantum point contact, or a resonant transmission. This could be a quantum dot, for example. And here is what I was saying before. So the non-equilibrium distribution here at these 2 points in the density plot look like this. So they are a mixture of thermal distribution, by themselves are non-thermal. And in the density plots, where the green region represents the parameter regime where the system can operate as a daemon. So you can produce a finite output power. And instead, this blue region here is when it does not. And finally, the yellow region is where, so what I mean, when I say it does not, I mean that it does not produce any power. So it's rather dissipating rather than producing a power. And instead, the other region is where you cannot meet the conditions by which you can impose that the currents between the system and the daemon are 0. Okay, so because for every combination of transmissions and biases that you choose, you have to kind of impose that there is no current between the system and the daemon, and this is not always possible, especially when you go into the nonlinear regime. And okay, here is how the power looks like. And here, what I was saying before, the entropy production in the daemon is positive, which explains why you can instead reduce the entropy in the working substance. All right, so then what about the fluctuations? Finally, we come to the final point. So the first thing to notice is, let's write down what are the fluctuations of the incoming current from the non-equilibrium part into the working substance. So you can do the calculation and you find this expression here. And remember, this tau int is the probability, is the interface transmission function. So the first thing that you notice is kind of an obvious result, is that these fluctuations have to be present for the system to work the way we want, because the only way this quantity is 0 is when the interface transmission is 0, which means that the system is completely decoupled from the non-equilibrium resource, and therefore all the currents that will flow between 1 and 2 have to go according to the second law. So the system cannot work. So in this sense, fluctuations have to be present for the system to work. So the second thing, okay, yeah, so this is what I said, and also this kind of reasoning can be extended to whatever combination of reservoir. You just take a multi-terminal system, let's say one of them provides the non-equilibrium and all the other ones are just your working substance. This reasoning also extend to this more complicated system. Second thing, important one, is actually unlike what happens for the average currents, you cannot map the two systems onto each other when you start calculating fluctuations. And that's just because, I mean, the noise doesn't behave like the current, and it will mix the different terminals in a different way. So only in very specific conditions this is possible. And I mean, we are still trying to work out what are the most general conditions under which this mapping is possible, but just to give an intuition, is basically where you cannot mix the distributions of 3 and 4 at the same energy. So you have to completely separate them. And let's say for a given energy interval, I only take 3. And for the complementary energy interval, I take 4. So there is no mixing at the same energy. And so if this is the case, then you can kind of show that you can effectively map also the noise just by an effective description. Okay, so this is just to say that we need to know, if we want to characterize the noise, we need to know how the non-equilibrium resource is implemented. But it makes a difference whether you just say, you give me whatever funnily shaped non-equilibrium distribution, or you just construct it this way, for example, with mixing two thermal states. So it's very much dependent on how you implement the system. So we took an example. So we took this system here, which is kind of more under control, because it's easy to start with the system when you just mix 2 thermal states rather than taking whatever arbitrary function to describe your non-equilibrium state. So we choose a specific implementation. We specify the conductor's properties. So this means how the transmission functions in the system look like. We determine some parameters that will fix and guarantee that on average you don't transfer any current between the 2 subsystems. So that would be in the next plot, that would be mu4 and mu3. These are fixed by solving these equations. And we calculate what is the input noise, and by that I mean the noise in the current that is exchanged by the 2 systems. The noise, for example, in the output quantities, that could be the cooling power and so on. So this is an example. Whenever you see white, the system does not work. So this is a refrigerator implementation. And so we want to cool terminal 2. Sorry, of course, this should be a minus, of course. So we have terminal 2, which is colder than terminal 1, and we want to cool it further. So this should be T0 minus delta T. In this case, the output quantity is the cooling power, which is the heat current leaving terminal 2. Okay, so this is shown in this top right panel for a given combination of transmission functions as a function of the temperature bias. And so what you can see is that you have a specific region that depends on the chosen parameters and on the chosen combination of transmission functions where the system can work. So where it's white, instead of having a positive cooling power, you have negative cooling power, so the system doesn't work. And we compare this with the input fluctuations, that would be this top left, and with the output fluctuations. And so the first thing that we notice here is by looking at the scale, is that it's so input and output fluctuations are not very much related in the sense, for example, it's not always the case that the fluctuations in the output quantity are larger than the fluctuations in the input. So that's one first thing. And also, by looking at other configurations, for example, when you try to run the system as an engine, you can show that there are situations where basically the input noise is very weakly dependent on the system parameters, but still the output quantity can vary by a lot. So here, more than an order of magnitude. So this means that just by calculating the noise brute force, there is not a direct, rather, apart from saying there has to be noise, otherwise the system doesn't work, there is at the moment not the direct link with, for example, let's say you have more input noise, so you have more fluctuation, and therefore you are producing more power. So this is not the case, which brings us to the question where we are working on at the moment, which is to identify which is the relevant part of the noise. Because apparently these results show that not all the fluctuations are kind of converted into some useful output. And so we are trying to understand whether we can define some combination of noises or parts of it that are directly related to the useful quantity in the system. So I would say that this brings me to the conclusions. So in the first part, I have discussed in a simple two-terminal device how to characterize the non-equilibrium fluctuations. So focusing in particular on the shot noise. And I have I have shown how some bounds can be derived that will basically limit the non-equilibrium part of the noise to be always smaller than the thermal fluctuations, and that this does not work for heat and energy transport. And in the second part, with this non-equilibrium demon, the results we have so far say that of course there has to be noise for the device to work, and then the actual outcome in terms of how the noise looks like is very much dependent on the device realization. So it's not the same just to have a description with 3, 4, or many more terminals. And there is, in a sense, high tunability in the system. So there is no direct link between the fluctuation and the power production, which on the one hand means that we still have to do some work to understand it better. On the other hand, it says that it's actually not necessary to have large fluctuations in absolute sense to produce any useful output. So for the outlook, in this first part, I've discussed the role of thermal and shot noise in a non-interacting model. So natural question would be to then address what is the role of interactions and how this affects the bounds that I have discussed. And also, there has been this paper few years ago, where they have derived in an out of equilibrium situation a fluctuation-dissipation theorem, and there this is done in like master equation with a master equation approach, and under the condition that in a part of the system there is a sub part of the system where zero current is achieved, then basically you can derive a fluctuation-dissipation theorem in the vicinity of this point. So this point at zero current is not in a global equilibrium situation, but it kind of becomes the point around which you can have fluctuation-dissipation theorem, just as the equilibrium one is a bit modified. So we wanted to the next step also in this part would be to understand whether we can extend this result to the system that we are investigating. And for the demon part, as I said, we're trying to identify which are the relevant fluctuations and whether they can be linked, for example, with information flow, because, or if this is possible to define it in the system that we have, because after all, it kind of behaves like a demon. So that would be it for my part. I just want to take a minute to advertise some open positions at Chalmers.
Jobs, yes.
So yeah, I was asked to do that. So in particular, there is a postdoc opening in Janine's group in collaboration with the experimental group of Witlef Wieczorek at our department. And it's about theory of quantum systems and nonlinear quantum optomechanics. So it will be in close collaboration with the experiments they are doing in optomechanics. Yeah. So I mean, if you know someone interested, please just let them know of this opportunity. Thank you.
Very nice. I have a question about the last part. So there is this notion in the field of quantum dynamics of passivity of quantum state.
Passivity of quantum state. Yeah, I'm not sure I know exactly what it is.
Yeah, basically it means that if you have anything that deviates from a thermal distribution,
yeah,
such that you have such that if there's a way of operating on it to extract work from it, this is a possibility. it sounds like from your non-equilibrium distributions that you were writing down, you had in principle that possibility. Now, whether the way you implemented it in terms of the refrigerator was the optimal one so I guess my question is, do you think if you had a better geometry or a better way of extracting energy, that this would be possible in the situations you were showing no refrigeration?
That's very possible, because I mean we are trying simple combination of how the scatterers are placed. So yeah, okay. So I mean this configuration of transmission functions is not, of course, the most general. The point is that we are going for this kind of asymmetric configuration, because this allows us to more clearly identify what's coming in here at this dot. Because if you just write down whatever scatter metrics, it's a bit more complicated to actually define what the input, because everything is connected. So the advantage of this thing is to kind of be able to say that what comes in is this mixture of thermal distribution that was mentioned. But sure, even in this simple configuration, you have different choices for the transmission. So you have kind of a lot of parameters, which is why we're not sure that we are doing it in the optimal way at the moment. Yeah, so that's, but yeah. Another thing that we are trying to understand is, let's say we come back to this scenario here, where you just say, okay, there is something, and we write it like, for example, as a thermal plus some small deviation, and try to understand whether we can make some statements on a more general level, being a little bit agnostic on how this is implemented. So this is another thing we are trying to understand at the moment.
And you must know my earlier paper with Rolf about the 3-terminal version
Yes.
of this.
Yeah.
Did you try to look at this this kind of simpler 3-terminal geometry for your?
But if I remember that 3-terminal geometry, the point is that you do have energy exchange, right?
Yeah.
Between, yeah. So in that case, you're still kind of providing something from
I see.
one part to the. So we don't want to do that, because we like this idea of having kind of analogous system to kind of daemon, which is working. So actually we are building up on another thing is basically to combine the paper that you have with Rafa with an extra terminal, and basically compensate with the other for the energy that you exchange. And there the system has interaction. So yeah, we are trying to understand.
Okay, good. All right, last talk of the conference.